Okay, so let me make a start. So today I'm going to introduce the Thermal and Statistical Physics 1 class, or Yolmit Tongin Mulihak. If you're wondering why we're in this lovely lecture theatre, it's because this class is going to be recorded. If you look at the back, there are 2 cameras which are recording what I'm doing. So this class is going to be recorded and then later uploaded onto Cyber Campus, but I'll talk a bit more about that later. Okay. So there are 2 topics in this class. The first is thermal physics, and the second one is statistical physics. Thermal physics is the study of heat and temperature. So how does temperature affect a physical system? And statistical physics is the study of the statistics of particles in a system. So how do particles in a system behave? So these are 2 separate topics, but as we will see in this class, they're very closely related. In fact, we can define thermal physics in terms of statistical physics. Okay. Thermal physics was very important in the development of things like steam engines, which had a driving role in the Industrial Revolution about 150 years ago. So today I just want to introduce a bit of the theory and a bit of the history. And to do that, I've got some devices here which I'm going to explain as we go through. So this first one is a thermometer. Okay? The first thing you need to do in thermal physics is to be able to measure temperature. So this is a thermometer which will do that. And these second 2, let me see if I can start this one going. Okay. These 2, this one is called a drinking bird for obvious reasons. And this is called a Stirling engine. These are examples of heat engines. They use a difference in temperature to do useful work in exactly the same way as a steam engine uses the heat generated by boiling water to do work. Okay. So today I'm going to explain how some of these things work. Okay. So we'll start with an introduction to the history of thermal physics. One of the things which is interesting is that temperature and heat are quite intuitive concepts. If you touch something, you know whether it's hot or if it's cold. So we have a very simple grasp of heat and temperature. But even though that's true, it took a long time before we were able to quantitatively measure temperature. That was first done in about the 15th century. And even longer in the 19th century, when scientists really understood what heat and temperature are in terms of the physics. So, as I said there, 15th century was the first time that temperature was measured. This is, as I said, a device to measure temperature. Then the first systems, why do you want to measure temperature? You want to measure temperature because the temperature of a system affects its properties. If I have water at, say, 20 degrees, and I have water at minus 20 degrees, those systems are very different. One is ice and one is liquid. Right? So we want to understand how does temperature affect the properties of a system. Now the earliest examples which were discovered were for the properties of gases, because gases behave quite simply as you change their temperature. For example, there's this thing called Amonton's law, which says that if you have a gas in constant volume, so I keep a gas in a box, and I measure its pressure is proportional to its temperature. So the hotter the gas gets, the more pressure the gas exerts. Okay. Then in the 18th and 19th centuries, these observations were slowly formulated into a general theory of heat, which is known as the theory of thermodynamics. But it wasn't until the 1840s that it was really understood that heat is a form of energy. For a long time, people thought that heat is a kind of fluid which flows from hot things to cold things. So if I have a block of wood and I burn it, then they thought that the fluid of heat is escaping from the wood, for example. Okay. But James Joule in the 1840s did a series of experiments which eventually showed that heat is just energy, just like kinetic energy or potential energy. And then a few years later, in about the 1870s, it was eventually shown how you can define temperature in terms of the properties of the particles of the system. And this is the connection between the statistical physics and the thermal physics. And that's what we will finish this class with. Okay, so I'm just going to briefly introduce some of these devices. How do we measure temperature? The first temperature measuring device was called a thermoscope. This is a diagram of it from a very early book. The idea is very simple, so I just want to explain it. So you can see from the diagram you've got a ball at the top. This ball is filled with air, surrounded by glass, and this goes down in a thin tube into a kind of bowl which is filled with liquid, say water. Okay? And there's some level of water in the tube. Now, there's some pressure in this system. The first pressure is that there's atmospheric pressure. The air outside is pushing down on this water and trying to push it up in the tube. But the air inside the tube is also pushing down. Okay? Now, if we assume that the atmospheric pressure stays constant, but we change the temperature of the air, then as I said, the pressure is proportional to the temperature. So if I heat up the air, the temperature increases, the pressure increases, and that will push the liquid down. Okay? If the temperature goes down, then the pressure goes down, and that will pull the liquid up. Okay? So by measuring the height of the liquid in the tube, you can measure the temperature. Higher up means colder, lower down means hotter. Okay? This is called a thermoscope. Okay? So I also mentioned that James Joule eventually showed that heat is a form of energy, and he did this in a series of very nice experiments, which again I want to explain briefly. How do you show that heat is a form of energy? Well, this is a diagram of one of his experiments at the bottom here. Inside here you've got a box of water, okay, and this is a thermometer which is measuring the temperature of the water. It's attached to this rod here, and then a string goes from the rod over this pulley and down, and is attached to a mass. So what you do is you let this mass go down, and as this mass goes down it pulls the string, and the string turns this handle here. And as the handle turns, you can see down here there are lots of little paddles. These stir up the water. So as the mass goes down, these turn around and they mix up the water. And if you wait long enough, you find that the temperature of the water increases. Because you're stirring it, you're increasing the temperature of the water. So what Joule did is he measured how far does the block go down. That tells you the energy, right? Because the energy is mass times the height times the gravity constant. So how much energy does go in, and you measure the change in temperature. And what you find is there's a direct relationship. The amount of energy you put in is proportional to the change in temperature. He then did a similar experiment, whereas instead of using gravitational energy in this mass, he used electrical energy. So he used an electrical circuit to heat water, and he found exactly the same relation. So whether you use gravitational energy or whether you use electrical energy, the change in temperature is always the same. So what this shows is that the energy that you're losing here when the block goes down or when you use the electrical circuit is going into the water, and the change in temperature is a result of the change in energy of the water. So therefore we can say that heat itself is a form of energy. Okay. So that tells you a bit about the background of the theory. How do we measure temperature and what are some of its effects? What can we do with this knowledge? And I've already said the most important consequence of thermodynamics was the development of heat engines. For example, the steam engines, which revolutionized the world about 150 years ago. So the principles which drive steam engines are very similar, or the same, as the principles which drive the internal combustion engines, which are inside most cars today. So it's exactly the same kind of ideas. The mechanics has got more sophisticated, the technology has got better, But the same idea that explains how this works also explains how this works. And also explains actually how this little bird drinks as well. Now what heat engines do is, inside any heat engine, you have a hot place and a cold place. Right? For example, in a car, the engine is hot and the outside is cold. And the heat engine uses the transfer of heat from the hot place to the cold place to extract energy. So as the heat flows from the engine of the car to the outside of the car, we can get some of that energy out and use it to drive the car. That's the basic principle. The same is true in a steam engine, and the same is true in this bird. In this bird, the head is colder than the body. Okay? And it's the difference in temperature which makes the bird move. You can also take the same principles and run it backwards. If you do the same thing backwards, then instead of taking energy out, you put the energy in, and then the heat goes from the cold place to the hot place. So by putting energy into the system, we can force heat to go from a colder place to a hotter place. And this makes the cold place colder and the hot place hotter. Right? So examples of this are air conditioning systems. You want the inside of your house to be cool, so you want to take heat out of the house and put it outside where it's hot. So it takes energy in and it moves heat from the cold place to the hot place. The same is true of refrigerators. They take heat out of the inside of the fridge and put it out. So in this class we're going to study how these kinds of systems work. What are the physical principles underlying these systems? So far I've explained quite thoroughly the first part of this course. We're going to start by looking at the laws of thermodynamics. Then we're going to look at some classical systems. We're going to look at heat engines like these. And we're going to look at the properties of gases. And finally, we'll talk about their effects in the Industrial Revolution. Okay. The second part of the course is the statistical part. I'm not going to say too much about this now, but just to motivate it, imagine, say I've got a gas. So that means I've got a box which is filled with particles, and each of these particles is moving in a certain direction. Okay? Now suppose I know the position of each particle and the velocity of each particle. This gas has a certain temperature given by T. Okay? T is the temperature. The question is this T an extra piece of information from all of the velocities and positions of all the particles? For example, specifically, if I tell you the position and velocity of every particle, can you tell me the temperature? Okay. And the answer to this question turns out to be yes. If you know the state of every particle in the system, you can also define what's the temperature of that system. And the way you do this is statistical. You look at all of the possible positions and velocities of the particles, and then from this ensemble, as it's called, you can derive the temperature. Okay. So that's going to be the whole idea of the second part of the course, explaining this connection between the microscopic behavior of the particles and the temperature of the system. Okay. Books. I do not use a book for this course. I've developed it in my own way, but I will give out notes each week. So each week of the course I will give you out a little summary note which will explain everything we're doing in the course. So you don't need to buy a book, but if you want to, then these are some of the books I used when I made this course. So if you want to get a book, these are some suggestions, but it's your choice. Right, so that's the end of the introduction. I just want to do one more thing before I finish. I want to explain how some of these things work. This thermometer I will explain in the next class. Okay? This bird is actually quite complicated. The way it works is quite complicated. So we'll probably explain this in about 2 or 3 weeks. Okay? So I want to start by explaining this one, which is called the Stirling engine, which is probably the simplest one to understand. So if I draw a very simplified diagram of what the Stirling engine looks like, hopefully you can see it there, or on the paper. You've got a chamber which is filled with gas here, okay? And there are two pistons which go into the chamber. The first one is a big one, which is this blue one here, which covers virtually all of the area of the chamber. So that goes up like that. And the second one is this smaller little black one, which you may be able to see here, which fits in a position like this. Okay? And these go up and down. Okay, so there are two pistons, and they have different roles. This one is called the displacement piston. And this one is called the drive piston. Now what's important, I said that heat engines always use a difference between hot and cold. Right? This machine is currently running on a cup of hot water. Okay, so there's hot water in there, which means that the bottom here is hot, and the top here is cold, or at least colder. Okay, so there's a temperature difference. Now, as this big displacement piston moves up and down, it pushes the air either towards the cold part or towards the hot part. Okay? So in the first picture on the presentation, I've tried to capture it here. The piston, displacement piston, is right at the bottom. Okay, it's right at the bottom. That is blocking the hot part of the system. Right? That means that the gas inside here will become colder, because it can't touch the top hot part, it can only touch the cold part. So the gas becomes cold. As the gas becomes cold, it tries to contract. Okay? It tries to contract. In order to contract, it has to pull the drive piston down. So the gas pulls the drive piston down, and you can hopefully see the drive piston is connected to this big wheel which is going around here. Okay? So as it pulls the drive piston down, it pulls the wheel down. Okay? And that makes the wheel go around. Okay. So in summary, it's a process in which the gas gets hotter and colder as driven by this displacement piston. As it goes up and down, the gas gets hotter and colder. As the gas gets hotter and colder, it expands and contracts. And as it expands and contracts, it drives the drive piston up and down. And the piston going up and down makes the wheel go round and round. So that's a summary of how it works. So just in case you couldn't see it very well, I made a video in the next slide. So I did just want to say one more thing about this system before we finish. The amount of heat in this system depends upon the temperature, okay? How much hot it is. But the amount of energy you can get out does not just depend upon the temperature. The critical thing is the temperature difference between the hot and the cold. If these were the same temperature, then it doesn't work. Even if they're 1,000 degrees, if they're the same temperature, it doesn't work. So you can't just get the heat out from a system with a high temperature. In order to get the heat out, you must put a high temperature system in contact with a low temperature system. Okay? So it's the difference in temperature which is important. And I wanted to illustrate that here, that you can also run this machine on ice, hopefully. So this is an ice pack. So now I've reversed the whole thing. Once you put it on ice, the top part is now hotter, and the bottom part is now colder, but hopefully you see it runs just the same. So it's not the high temperature that's important, it's the temperature difference which is important. And one of the important results we'll prove in the course is that the maximum amount of energy you can get out depends upon the temperature difference. Okay. Right, so that really is the end of this course then. I hope that sounds interesting. So in the next class we're going to start very simply looking at some definitions of how temperature is measured. For example, I'm going to explain how this thermometer works. If you have any questions about this course, you can always come and find me in my office or send me an email or call me. So I'll finish there. If you want to come and look at these things, by the way, once the class is finished, you can come and have a look. I don't mind, it's up to you. Okay, thank you.